Quantum mechanical model of atoms. A new branch of science called quantum mechanics was developed in 1926 by Werner Heisenberg and Erwin Schrödinger based on uncertainty principle and wave motion respectively. Quantum mechanics based on the idea of wave motion will be discussed here. Schrödinger developed the fundamental equation of quantum mechanics which incorporate wave particle duality of matter. The Schrödinger equation or wave equation is written as h bar wave number is equal to E wave number. Here h bar is a mathematical operator called Hamiltonian. Psi is the wave function, E the total energy of the system. Solving Schrödinger equation is beyond the scope of this book. It may, however, be noted that the solution of Schrödinger equation gives E and wave number and wave function psi. 47.1 Schrödinger equation. When Schrödinger equation is solved for hydrogen atoms, the possible value of energy E that the electron may have along with the corresponding wave function psi are obtained. As a number, as a natural consequence of solving this equation, a set of three quantum number characteristic of quantized energy level and the corresponding wave function are obtained. These are principal quantum number n, azimuthal quantum number L, and magnetic quantum number ml. The solution of Schrödinger wave equations led to three quantum number and successfully predicted feature of hydrogen atom emission spectrums. Splitting of spectral line a multi-electron atomic emission spectra could not be explained through such model. These were explained by George Uhlenbeck and Samuel Goldsmith 1925, who proposed the presence of fourth quantum number called electron spin quantum number ms. Wave function psi as such does not have any physical meaning. The probability of finding an electron at a point within an atom is proportional to psi square in the neighborhood of that point within a tiny volume element around it. 4.7.2 Atomic orbital and quantum number. Many wave functions are possible for an electron and therefore many atomic orbitals are present in an atom. Thus, the wave function of atomic orbital form the basis of the quantum mechanical electronic structure of an atom. Various orbitals in an atom differ in size, shape and orientation with respect to the nucleus, depending upon the value of psi square. Each orbital is designated by three quantum numbers labeled as N, L, Ml, and each electron is being assigned with four quantum numbers is N, L, Ml, and Ms. The principal quantum number n is a positive integer with value of n being 1, 2, 3, 4. It identifies the shells. Atomic orbitals have the same value and belong to the same shell. With the increase of n, the number of allowed orbitals in that shell increase and is given by n square. A set of orbitals with given value of n constitute a single shell. Shells are represented by symbol K, L, M, N, and so on. See table 4.6. Table 4.6. Allow orbitals in the first four shell. Principal quantum number n. Shell symbol. Allow number of orbitals n square. Size of shell. N is 1. Shell symbol K. Allow number of orbitals 1. Principal quantum number n is 2. Shell symbol capital L. Allow number of orbitals is 4. Principal quantum number n is equal to 3. Shell symbol capital M. Allow number of orbitals is 9. Principal quantum number 4. Shell symbol n. Log number of orbital is 16. Size of shell is increasing. From 1 to 4, size of shell is increasing. With an increase of n, the distance from the nucleus and size of the shell increase, and also the energy increase become lesser and lesser negative. In hydrogen-like species, the energy of orbiter depend only on the value of n. In the case of multi-electron atoms, the energy of orbiter depend on two quantum numbers, n and l as well. The azimuthal quantum number L is also called subsidiary quantum number. Atomic orbital with the same value of n but different value of L constitutive or subshell belonging to the shell for the given n. The number of subshell in a shell is equal to n. Thus, the third shell contains 3 subshells with 3 different values of L. The second shell contains 2 subshells and the first shell contains only 1 subshells. The value of L range from 0 to n minus 1, whereas the K shell with n equal to 1 contain only 1 subshell having L equal to 0. The subshell or sublevel having L equal to 0, 1, 2, 3 are presented by the symbol S, P, D, F respectively. Table 4.8. Show orbiter in the first 4 shell with the 3 quantum number for each orbital. Orbital distribution on first 4 shell. Symbol of shell K. Value of principal quantum number n is equal to 1. Number of subshell 1. Value of azimuthal quantum number L is equal to 0. Symbol of subshell is 1s. Total number of orbital in the subshell is equal to 2l plus 1. 2 multiplied by 0 plus 1 is 1. Value of the magnetic quantum number ml for the subshell is ml is equal to 0. Symbol of shell L. Value of principal quantum number n is equal to 2. Number of subshell is 2. Value of azimuthal quantum number L is 0. Symbol of subshell is 2s. Total number of orbital in the subshell is 2l plus 1 is 2 multiplied by 0 plus 1 is 1. ml is equal to 0. L is equal to 1. Subshell symbol is 2p. 2 multiplied by 1 plus 1 is equal to 3. So ml is equal to minus 1. ml is equal to 0. ml is equal to plus 1. m equal to n equal to 3. 3l equal to 0. 3s. 2 multiplied by 0 plus 1 equal to 1. ml equal to 0. L equal to 1. 3p. 2 multiplied by 1 plus 1 equal to 3. ml is equal to minus 1. ml is equal to 0. ml is equal to plus 1. L equal to 2. 3d. 2 multiplied by 2 plus 1 equal to 5. m equal to minus 2. m equal to minus 1. ml equal to 0. ml is equal to plus 1. ml is equal to plus 2. n equal to 4. Number of subshell is 4. Value of azimuthal quantum number is L equal to 0. Symbol is 4s. 2 multiplied by 0 plus 1 equal to 1. m equal to 0. L is equal to 1. 4p. 2 multiplied by 1 plus 1 equal to 3. ml is equal to minus 1. ml is equal to 0. ml is equal to plus 1. L is equal to 2. 4d. 2 multiplied by 2 plus 1 equal to 5. ml is minus 2. ml is equal to minus 1. ml is equal to 0. ml is equal to plus 1. ml is equal to plus 2. L is equal to 3. 4f. 2 multiplied by 3 plus 1 is 7. ml is equal to minus 3. ml is equal to minus 2. ml is equal to minus 1. ml is equal to 0, ml is equal to plus 1, ml is equal to plus 2, ml is equal to plus 3. 4.9. How many orbitals make the end shell? What is the subshell-wise distribution of orbital in the end shell? Solution. For n shell principal quantum number n equal to 4. Therefore, total number of orbitals in n shell is equal to n square is equal to 4 square equal to 16. The total number of subshell in n shell is equal to n equal to 4. The four subshell with the azimuthal quantum number and constituent orbital number are as shown below. Azimuthal quantum number L. L is 0. Symbol of subshell is S. Number of orbital 2L plus 1 is 2 multiplied by 0 plus 1 is equal to 1. Azimuthal quantum number L equal to 1. Symbol of subshell is P. Number of orbital is 2 multiplied by 1 plus 1 is equal to 3. L is equal to 2. Symbol of subshell is D. 2 multiplied by 2 plus 1 is equal to 5. Number of orbital. Azimuthal quantum number L is equal to 3. Symbol of subshell. Number of orbital 2L plus 1 is equal to 2 multiplied by 3 plus 1 equal to 7. Boundary surface diagram 1s 2s. Shape of 1s and 2s orbital. Frequency 4.7. V. Show the boundary surface diagram of atomic orbital 1s and 2s, which are spherical in shape. Here, boundary surface is round in shape on an orbital, such that the value of probability density psi square is constant and enclose a region where the probability of finding electron is typically more than 90%. Such a boundary surface diagram is a good representation of shape of an orbital. Problem 4.10. An atom has 2 electrons in its 4s orbital. Write the value of the 4 quantum number for each of them. Solution. For the 4s orbital, 4 stands for principal quantum number n, S stands for subshell, S having the value of azimuthal quantum number L equal to 0. In the S subshell, there is only one orbital and has magnetic quantum number ml equal to 0. The 2 electrons in the S orbital have opposite spin. Thus, 4 quantum number of 2 electrons in 4s orbital are electron 1 n equal to 4, L0, Ml0, Ms is plus 1 by 2. Electron 2 n is equal to 4, L is 0, Ml equal to 0, Ms is minus 1 by 2. Do you know the value of psi square at any finite distance from the nucleus is never 0? Therefore, a boundary surface enclosing 100% probability density which occur only at the infinity cannot be drawn. The s orbitals are spherical in shape. Their size increases with increase of an n. It means that the electron located further away from the nucleus as the principal quantum number n increases. 2pxz, 2pyz, 2pz. Shape of 2p orbital. Figure 4.8. Display the boundary surface diagram with the nucleus being at the origin. For the 3 2p orbital n equal to 2 and l equal to 1, it can be seen that each p orbital has 2 lobes on the 2 sides of a nodal plane passing through the nucleus. A nodal plane has psi square very close to 0. The size and energy of the dumbbell shaped 3 2p orbital are the same. Their rotation space are however different. The lobes of the 3 2p orbital are along the xyz axis. Accordingly, the corresponding orbital are designated as 2px, 2py, and 2pz. The size and energy of orbital p subshell increase with increase of principal quantum number dxy, dxz, dyz, dx square, y square, dz square, shape of 3D orbitals. There are 5 orbitals associated with d subshell, designated by dxy, dyz, dxz, dx square, y square, and dz square. The shape of 5 3D orbitals are shown in figure 4.9. In spite of difference in their shape, the 5D orbitals are equivalently energy. The shape of 4D, 5D, 6D orbitals are similar to those of 3D orbitals, but their respective size and energy are large, or they are said to be more diffused. 4.7.4 Energy of orbitals. The energy of an electron in the hydrogens or atoms or hydrogen like species determined by the principal quantum number alone. This is because the only interaction in this species is attractions between the electron and nucleus. An increasing order energy orbital in the hydrogen atom is given by 1s smaller than 2s equal to 2p smaller than 3s equal to 3p equal to 3d smaller than 4s equal to 4p equal to 4d equal to 4f smaller than, of course. The shape of the concerned SPDF orbital are different as described earlier. The orbital with the same energy and corresponding wave function being different are called degenerate orbitals. Thus, in hydrogen atom, 2s and 2p are degenerate orbitals. In the multi-electron atom, there is mutual repulsion among the electron. The energy of an electron in an multi-electron atom therefore depends both on the principal quantum number n and azimuthal quantum number L. The lower the sum n plus 1 n plus L for an orbital, the lower is its energy. If two orbitals have the same n plus L value, the orbital with the lower value of n is of lower energy. This is called n plus L rule. From the n plus L rule, the increasing order of energy of orbital in multi-electron atom can be written as 1s smaller than 2s, smaller than 2p, smaller than 3s, smaller than 3p, smaller than 4s, smaller than 3d, smaller than 4p, smaller than 5s, smaller than 4d, smaller than 5p, smaller than 6x, smaller than 4s, smaller than 5d, smaller than 6p, smaller than 7s.